I see some more people kind of trickling in. But we'll get started on time. My name is Emad Benjamin. I'm a principal engineer with VMware. And alongside of me is Guillermo Tantachuco. He's a senior field engineer with Pivotal. We're going to be talking to you about virtualizing and tuning large-scale Java platforms. As we kind of peel the various layers of the onion here, we'll get into more detail throughout the session. A little bit about ourselves. Guillermo's been in this for about 18 years. He's a hands-on, up and down the stack field engineer, Spring, VFabric, Pivotal products, big data, fast data, and so on. And he was also 2012 President Club winner. All right. Myself, I've been in this for about 20 years. I've been focusing on Java for about 15 years. And a couple of shameless plugs there for my books. All right. So here's the agenda. Now, this is a watered-down version of an all-day workshop that I run. Sometimes it's 2-3 days, where we try to engage with our customers and make them into better JVM tuners. We're going to try and attempt a version of that here today. Certainly through the slides, we'll show you how to GC tune, show you the recipes that I apply and have been applying. But also, we're going to show you a demo. So probably halfway through the session, we're going to switch over to demo. Guillermo will come over here and kind of walk us through a demo where we've been working on in terms of adjusting some of the flags, some of the JVM flags. We're going to run a JMeter on it and show you the results. So today's agenda will be an overview. We're going to get into design and sizing. Single most critical thing about Java platforms is knowing how to size them correctly, right? And then we're going to talk about performance, whether it's virtualized or not virtualized. What's the story behind performance? So we're going to show you some performance studies. We'll talk about best practices and GC tuning. Again, we'll switch to the demo, and then if we get time, we'll show you a couple customer case studies, and then we'll open up to questions. I take questions throughout. You know, you guys can ask as many questions as you want, so feel free. With that, let's begin with first the overview of Java platforms. About 3 years ago, I was asked to kind of define what a Java platform is, and I kind of looked back to the many years I was engaged in troubleshooting and trying to design Java platforms, and I realized that I spend most of my time across these 4 technology layers. First, you've got the load balancer tier, the web server tier, the Java application server tier, and the database server tier. As a Java DevOps person, developer/ops guy, you really are the glue across all of these technology tiers. Why? Because you can't really talk to a DBA and say, hey, I've got this Java problem. You need to adjust DB connections, right? You're the one carrying the ball. So as a Java reliability engineer, you need to kind of know and be cognizant of all those 4 tiers. And when you're designing as well, you need to know how many transactions are arriving at the load balancer, how many web server instances you need, how many Java application server instances, JVMs you need, and how many database connections. Again, complicating this, you've got the load balancers with the networking team. You know, they don't even know what a Java developer looks like, right? And then the web server team, they're probably, if it's an Apache instance, they're probably part-time Linux guys that have kind of along the way learned Apache. Again, deep tuning, they're going to turn to the Java engineer to try and figure some of the tunings out, and then the Java application server and so on. So you carry the ball, and as a result, in this session, we talk about all of those 4 layers and give you some of the learnings along the way. What am I seeing in the market? I'm seeing actually load balancers being virtualized. I was pretty surprised. About 2 months ago, I was talking to a military customer. They had one of those load balancers virtualized. So F5 comes in physical and virtual. Zeus is only virtual. And nice thing about that is you can apply, you know, various fault tolerances and HA functionalities to the load balancer, because the load balancer is a single line of defense. That goes down, your site is down. So you need to make sure that's robust. And we see plenty web servers out there being virtualized. Certainly that's the low-hanging fruit of the first tier to be virtualized, and then a slew of application servers. Okay, that was the high level. Now we get into the main section of the session on design and sizing. Literally almost every day I get a bunch of emails from customers attempting to do a performance study. But yet when I double click on the results, I find that they are really not comparing apples to apples. You know, they go from one platform, a different hardware configuration, to another platform. And in some cases, even code deployment has changed. Even actual code functionality has changed. And so what we try to do is spend time with our customers to say, learn step one, which is understand the behavior of the workload. When it's the peak, the traffic, the number of concurrent transactions, and so on. Whether you have good monitoring systems that measure that or you don't, you have to grab a bunch of log files to determine that. Either way, at kind of some point, you have to establish what the workload profile looks like. Once you understand that, then you model your load testing based on that. And it turns out that step two is basically vertical scalability test and a horizontal scale-out test. Whether it's on a virtual system or a physical system, you have to do that anyway. You need to know how big the JVMs will be, how many JVMs I need, and where's the sweet spot. And we're going to talk a little bit about that. And then if you're on a virtualized system, you could save a lot of those instances as templates, and then you build from those virtual machine templates. OK, so let's double click on step two, because that's kind of critical in load testing. In step two, what we're trying to establish is what's called the building block VM. Within this, we are going to determine whether we put one JVM instance, several JVM instances, how big are these JVM instances. So let's make the discussion a little bit easier and say we have one JVM instance on one virtual machine. And within this JVM instance, let's say the heap size was 4 gig, and the total VM had about 5 gig available to it, because you want to account for OS and some of the overhead outside of the heap. Let's say you did 100 transactions within this combination, right? You want to kind of mimic what your production deployment will look like. So if you've got war file 1 and war file 2 always go together, then you want to load test that. Don't micro benchmark it by load testing war 1 in isolation of war file 2 or application 1, application 2, because multiplexing applications does create a different JVM heap behavior. And so you want to be cognizant of that and make sure that it's multiplexed correctly. So you do vertical scalability test. Next, you do a horizontal scale-out test. OK, so here's like 30 seconds of virtualization 101, all right, in order to understand this. VMware virtualization, basically you take a physical server, you put the hypervisor on the actual hardware, and that allows you to spin multiple virtual machines that have their own compute space. So in this case, what we're doing is we're spinning up multiple VMs on a vSphere host, right? On a host that has a VMware hypervisor on it. In this case, I spun out 3 building block VMs. They're exactly the same size. Now, why are they exactly the same size? So if this is a 2 vCPU machine with 1 JVM, 4 gig heap, and so on, each one of these VMs is exactly the same. The reason why I do that is because I want to simplify my load balancer logic. The load balancer ideally will send equal amount of traffic to each one of those VMs. If the VMs are sized exactly the same, then basically the traffic is load balanced correctly. But if the VMs are sized as such, this is a 2 vCPU, that's 4, and that's 8 vCPU, then you have to adjust for that at the load balancer layer and say, I'm going to select a weighted algorithm to send 2x, 4x, and 8x amount of traffic to these VMs. Typically, I tell my customers, don't bother with that. Keep all the VMs exactly the same size, and choose a least connection-based algorithm for within the load balancer, and make life a little bit simpler. We Drive the load test basically up to 70–80% of underlying host CPU utilization. Beyond that, obviously, you don't want to run production beyond 80% CPU utilization, yeah, because you get some interesting overhead behaviors. We won't get into a lot of troubleshooting. I guess we'll do a little bit in the demo, but during the workshop, we go into a lot of troubleshooting. Now, you assume linear scalability when you're scribing this design on paper, but when it comes to actual testing, a bottleneck can appear anywhere at any point in time, whether it's at the building block VM, whether it's at the scale-out, or we're at the cluster-wide testing. And we have to eliminate that. And again, in the troubleshooting section, we talk about how to eliminate bottlenecks. I mean, the two key bottlenecks within Java-based applications, either you have a memory pressure somewhere, database contention, thread contentions, and so on. And we talk about how to look at each one of those. There are times I see that there's this section here. You have to go back and revise the building block VM. It could be that your Java developers or DevOps guys got a little excited and chose a 4 vCPU building block VM instead of a 2 vCPU and scaled out the middleware to a point where now the database layer is getting bogged down. You've essentially over-provisioned the middleware, and you have to go back and revise and constrain the middleware sizing. But essentially, your load testers should have this type of page in their test plans. If they don't, then they really are not approaching testing correctly. OK, in order to understand a little bit better in terms of sizing VMs and JVMs, let's take a look at a JVM process here in the brown box here, deployed on a single VM. Just keep it simple, one JVM to one VM for this discussion. There's some guest OS memory that's needed, and the Java process extent. Within the Java process, there's the heap. A lot of Java developers will tell you a significant amount of information about -XMX and what it does, but they don't tell you what's going on outside of the heap, but still within the Java process. There's initial heap, and outside of the heap, you've got the stack, the Java stack. So every time you execute anything within Java, you initiate a thread, -XSS is being allocated. Now, it is OS and JVM dependent, so if you say HotSpot on Linux, the default stack is 256K. Later on, I'll show you in category 1 type of workloads where we ideally don't want to kind of increase the stack. But in category 2, in-memory databases, we play around with the stack. We can go up to 4 meg sometimes. Outside of the heap, but still within the Java process, is the permgen area. This is where the class-level information of your application lives, and you have to statically size that. Eventually, this is going to be dynamic, and it'll help things along. And then there's this other obscure other mem section. Other mem section is where the internal JIT information is kept, where socket communication is kept. So like for every socket communication, you got a buffer for send and receive, and also direct buffers. So you have some in-memory products like cache products that bypass the heap, thinking they're being pretty smart about it, and allocating a lot of memory in this section. I don't recommend that. I recommend you build applications or products that leverage the heap, because the JVM continues to improve. You move with that improvement. So it turns out that we have this off the heap section and heap section. And again, Java developers kind of don't know really much about that, but JVM deployers need to know quite a bit about it, because it is a section that you cannot ignore. So it turns out that the VM memory required is made up of guest OS memory and JVM memory. And in turn, JVM memory is made up of the heap, the perm size, the size of the application, the number of concurrent threads times the stack. So if you've got 100 threads you're modeling, times that by the stack. And then this other mem section. Now, naturally, if you've got multiple JVM instances, you need to kind of provide a multiply here. The n is the number of JVMs. Pretty simple. Okay, so let's take a look at an actual sizing example. So here I have modeled a 4 gig heap, and I'm going to set the initial heap equal to the max heap. I always recommend you do that. There are instances where you don't if you're trying to kind of save on memory, but it's more pain than what it's worth, and ideally you want to set it equal to each other. In this case, I'm modeling about 100 concurrent threads. So if this was deployed on TC server, max threads is 100, right? And I've left the stack to default. In this particular application, 256 meg, it was more than enough to load all the classes. And then other mem section fudge factor comes in. This 217 is usually somewhere between 3% to 5% of this number, right? Now, if you have in-memory products that bypass the heap and deploy, use direct buffers, there could be that, that section of other mem significantly grow, but it never grows to, I would say, more than 10%, but you would have to test it. So it turns out that on average, if you've got a 4 gig heap, the entire Java process could be about 1.2, 1.25x of the heap. So when your Java developers talk about needing an application with about 4 gig, add about 20% to it in order to size correctly. And then we're going to allocate some memory to the guest OS, and it turns out that really to run this Java process, you need about 5 gig worth of memory. And if it's a virtual machine, what we do is set reservation. What set reservation does, it goes in and locks actual physical memory as if it's physical hardware. It takes the memory, allocates it to the VM, and says, do not ever take away this memory as long as this application is running on this VM. Again, these relative ratios kind of stay up and down, whether it's a larger JVM and a VM or a smaller one. And I'll show you other examples of larger JVMs. Here's one. For example, if we're talking about category 2 type of in-memory databases, typically the JVMs are large. Here I'm modeling a 30 gig example. Now, why 30 gig, right? It turns out that between 0 to 4 gig, when you move from 32-bit JVM to 64-bit JVM, there's basically pointer compression going on because the 32-bit pointer is essentially half the space of the pointer address space of 64-bit pointer. And compression in the HotSpot JVM works as such that 0 to 4 is 2 to 4, which is 32-bit space. So anything up to 4 gig is automatically compressed into 32-bit, but still running within the 64-bit JVM. Between 4 to 32 gig is opportunistic compression, meaning sometimes it'll do it, other times it won't. And beyond 32, it's off. It's completely off. Now, with in-memory databases, sometimes, let's say if you're sizing a 1 terabyte worth of in-memory database, right, and you divide that out based on 32 gig JVMs, that works out to be 30 plus JVMs, right? Well, it turns out that you could do away with the compression benefits of the compressed ops and size larger JVMs because you want to try and consume as much of the local available memory as possible and reduce the number of JVMs that you have in your grid. But we'll talk about that a little bit later. Sizing large JVMs, whether you're on virtual or not, you really have to know what the underlying hardware looks like. You can't really ignore it. And sometimes as Java developers, we say, just give me a server and go away. I know what I'm doing. You really cannot say that. You really cannot afford to say that if you want to really tune systems and platforms. Now, if you're on a physical system, obviously this section of the overhead is not, but let's assume you're on a virtual environment. Here we're trying to determine NUMA. And in a couple slides I'll show you what NUMA is, but the equation for NUMA is this. You take the total amount of memory, and then we take the overhead calculation. So this is overhead calculation. Every time you size a VM, there's about 1% overhead of memory that's required for the VM. And then ESX needs about 1 gig, and then we divide by the number of sockets. Okay? Here I'm showing you an in-memory database where what we've done is taken a 2-socket box and configured 2 VMs that fit nicely within the NUMA node right here in order to basically give the highest local throughput memory to this in-memory database, which is typically memory bound and memory hungry, right? Let me just, this is applying the equation. We've got 2 VMs, so there's about 2% overhead and so on. Now, keep in mind, sometimes you want to be careful about vMotioning heartbeat processes because there could be enough jitter that'll cause the actual data fabric to think that it's undergoing a split brain problem where, that you've got 2 clusters now. So usually we want to be careful when to vMotion a heartbeat process. Now in SQLfire, Gemfire, the heartbeat process is called locator. And other products, they call them different things. I have a list of them. Okay, so I want to explain NUMA now. The previous slides didn't really make that much sense until you get to this slide. Okay, so what is NUMA? So I have a 2-socket box here, and it's configured to have about 96 gig worth of RAM. Okay, this is each one of these procs or sockets have got 8 cores, 8 CPUs, 8 physical CPUs. The amount of memory that you've purchased is not really 96. It's actually about 47, because only 47 is configured within each NUMA node. So what happens if you size a process? Let's assume virtualization is not there. Let's say you put a Java process that's 48 gig. What will happen? What will happen is you get what's called NUMA interleaving. Because 47 gig is not enough to size that Java process, for that extra 1 gig, the OS is going to go to the next NUMA node and interleave. And that interleave process causes about 30% drop in memory throughput. It's a significant amount of memory throughput drop that you need to be cognizant of. You can't afford. So you want to be able to size within the NUMA node. Now, on a physical system, you have to use NUMA CTL and pin the process, the Java process, to the NUMA node, right? The problem with that is you got to keep doing that on a daily basis, right? Watch the load, do load testing, and figure out, am I pinned to the right NUMA node or not, and so on. Within ESX, it actually does that for you automatically. In fact, to the point where, let's say I've got a situation where I've got 4 VMs, all nicely pinned to the right NUMA node, all very highly local and so on. But then I get a situation where I get a 5th VM that doesn't quite fit within each of these NUMA nodes. Then ESX is smart enough to split the execution space, execute locally to each NUMA node to a point where it says, you know what, I can't do this anymore. I am going to interleave. So there are NUMA optimizations that are there coded into the hypervisor that otherwise are not on the physical OS, that you have to actually otherwise would, as an administrator, configure that yourself. And it's pretty painful configuration. All right. So let's talk about different categories of Java platforms. I work a lot with customers that have 6,000, 10,000. I have one insurance company that has 15,000 JVMs. And to me, it seems like, they build these systems out basically in the 32-bit days. And when they migrated the JVM container to 64-bit, the deployment paradigm of the application didn't change. They just took exactly how it was deployed and put it on 64-bit. Now, in 32-bit, we used to have the 1 gig JVM heap limit. In 64, we don't have that limit, right? But they never took a step back to consolidate the insane number of 15,000 JVMs. Really, do you really need that many? So I find what they're actually dealing with is these large Category 1 systems. And because they have a lot of JVMs, they end up tracking to being CPU bound before they are in-memory bound, right? Because every JVM will have its own GC cycle, and every GC cycle obviously chews up a lot of CPU. So it is important to kind of try and consolidate the number of JVMs and pick the right sort of hardware. Now, if you had a 256 gig box here, in order to consume all of the memory that's on that box, that's 57 JVMs. There's no way you're going to put 57 JVMs on a box that has only 16 physical CPUs. It's going to track CPU bound pretty quickly. So you either consolidate the number of JVMs or pick a 4-socket box, for example, that has more cores. Now, we take a look, and we did a performance study to prove this out. When you consolidate JVMs, do you really save on CPUs? Here, I've got a situation of 4 JVMs deployed on 4 2 vCPU VMs. Take these JVMs from the first scenario and collapse them into a total heap space of about 4 gig. So the net amount of heap is equal from option 1 here to here. But notice the VM is still 2 vCPU. Now, why didn't it go to 4 vCPU? Because originally it was 2 vCPU plus 2. The reason why it didn't go to 4 vCPU is because the GC cycle, once provisioned and takes up that overhead, it can keep on scaling vertically. This is why we can do large JVMs. The largest JVM I've done is a monitor, in terms of tune, is a monitoring system that was 360 gig. All right? I mean, and that's on HotSpot and Linux. Nothing fancy. We used PAR-NU GC and CMS in there, and we're able to get it to scale. Reason why it scales? Because GC has proven itself to be vertically scalable. And so we do the same here. And literally, if I've got 15,000 JVMs in this type of consolidation scenario, I could keep on going down to maybe 2,000 or 3,000 JVMs. Think about how much administrative cost, how much benefit you get out of that. So obviously, that's option 2. Now, there are some times where option 2 is not possible. You have to so why would option 2 not be possible? Option 2 assumes that the JVM instances within option 1 are all highly available pairs of each other. It's the same instance of the application, but you just needed more RAM, more memory, and you've kind of scaled out over the years. Consolidating is OK because you're not mixing in application life cycles. But there are times where you've got 1,000 JVMs. Each one of those JVMs is for a different line of business or set of line of businesses, right? And you can't really mix 2 lines of businesses together on one JVM because you take a foreign application 1 and another application 2 and put them together in the same JVM, that JVM crashes, you've impacted 2 lines of businesses, and you can't really do that. So we continue to see the JVM container as kind of the security zone for an application. OK, sometimes when you you have a 1 gig JVM and you scale up, deployers get lazy about basically deploying any Java application on there. So if it's a web application or a job scheduler or a batch system, they'll deploy it onto the same JVM. And within 1 gig, it might work fine. But you start scaling up, and you get into problems. Now, an alternative is to think about categorizing your workloads into JVM types. So you have a set of JVMs that deal with web applications, which care about response time, and job schedules, which don't really care about response time that much, but care about throughput. Category 2. Here we have an in-memory database. And typically with in-memory databases, we see a fewer JVMs. We're talking about less than 20 JVMs. It's not a hard and fast rule, but the fewer JVMs you have, the fewer network hops potentially, the chances are you're sizing JVMs that are large enough to occupy the whole NUMA node. And you should absolutely use up the whole NUMA node. Versus having to spin up way more JVMs and waste CPU cycles and additional JVMs due to the GC versus, hey, I'm going to spin up one JVM here. It takes the whole NUMA node, and I'm going to be able to vertically scale up, and we'll show you how to vertically scale up. Typically, in memory databases, we choose a 2-socket server instead of 4-socket, because for the same amount of money, we get larger NUMA nodes, more local memory. And then we're starting to see category 3 as a pattern appearing in the industry. I have a lot of customers that their platform, Java platforms, are starting to look like this. A bunch of enterprise applications, thousands of them, talking to a fewer backend JVMs. Now, here I'm modeling an in-memory database, right? But this could be a common services layer that the whole enterprise accesses. The services layer is not exposed to a user through a browser, not directly. It's exposed to the user through a browser through this system. But over here, it is a robust platform that you have to keep up. It could be your middleware and so on. And you have to kind of tune it as if it was an in-memory database. Within those platforms, we see larger JVMs, larger than 4 gig. OK, so let's talk a little about performance. Here we did a test on a workload driver called Oleo. It's a geocoder driver. We deployed it on TC server. And we wanted to see how far you can drive virtualization before the overhead of virtualization becomes an issue. So what we found is that when you get to about 80% threshold, so the brown is virtual and the blue is physical. And as you can see, we compare the overhead is really not that much. We compare fairly well to native. But beyond 80% CPU, the overhead starts to creep up a little bit. It goes somewhere between 5% to 8% on the CPU scheduler overhead, and as I showed you earlier, about 1% on memory overhead. Nobody cooks their Java platforms that well. So typically you will run within this range anyway. OK, so we did a performance study. Another performance study was, I have an application. I've done all the Java platform tuning on it that possibly can do, but yet the application is not really architected to go to the next level. And so Guillermo and I got together, and we put together a little exercise to mimic what our customer developers would do. We took a Spring Travel application and retrofitted it with using SQL Fire. We wanted to know how long this process would take, because some of the questions were getting, hey, this is like kind of code intrusive and so on. It really wasn't. But basically, we did this. Also, another thing is we did not tune anything. We made sure there's equal amount of compute space offered to the left hand and the right hand here to keep the test fair, because I'm pretty sure our customer developers would not go in and spend an insane amount of time trying to tune the JVM. Wanted to see quickly what kind of results you would get. Guillermo, you want to talk about this? Jump in here? OK.
So thanks, Emad. So the first thing that we needed to do in order for this application to work with SQL Fire was a couple of things. So first, we created a small SQL Fire cluster with allocator and a number of SQL Fire members. So we migrated, using the DDL utils Apache project, we migrated the schema from the relational database to SQL Fire. Now, on the client side, you guys are familiar with the Spring JPA. So all we needed to change was the JDBC driver. We also changed the connection string and the Hibernate dialect that corresponds to SQL Fire. And that's basically it. So the results that we obtained after running several tests were pretty encouraging. So if you take a look at this chart, we're just focusing now on performance results. And the y-axis represents the response time versus the number of threads, which is the horizontal axis. So the results in blue correspond to SQL Fire response times, and the results in red correspond to the response time of a relational database. So as you can see, the SQL Fire time remained constant, and there were about 5 milliseconds throughout the whole performance test, whereas the database actually took 172 milliseconds. So that's almost 30 times the time it took for SQL Fire to respond. Now, but we weren't happy with this, and we wanted to find out what was the breaking point of both systems given the same amount of infrastructure. So again, we took a look at the response time versus the number of threads, and we saw that the database broke at 1,800 threads, around 1,800 threads. So it couldn't keep, it couldn't keep up with the load. But on the other hand, SQL Fire actually kept up or scale up to 7,200 threads. So that's almost 4 times. And you see the inflection point. If you look at the blue line, you see the inflection point. That's because SQL Fire actually, when it starts hitting a threshold in the JVM memory, it starts spilling information to disk. So that, that gradually increases the response time. But if you provide more memory, you're going to get a much more consistent response time. Make sense? Now, if we want to find out, well, we wanted to find out how was the CPU utilization under, of this application under stress. So we found out that that the database stopped working at 80% of CPU, but SQL Fire kept going and taking, advantage of all the CPU that was available to it, and it took advantage of 98% of CPU. So, this table summarizes the test that we did. So we went from 18 threads to 7,200 threads. And as you can see in the red label, everything failed after a certain given number for a database. So what can we take away from this test is, first of all, we got 4 times the scalability compared, or with SQL Fire compared to a relational database. So you take 1,800 threads with the relational database and 7,200 threads with a SQL Fire instance, well, you're going to get 4 times the scalability. So that's a very nice scalability profile. So we were very, very happy with those results. If you take a look at the response time, so we got 5 milliseconds with SQL Fire and 172 milliseconds with the other database. That's almost 30 times faster for SQL Fire. So, again, the conclusion was that it wasn't a pretty expensive endeavor just to make that application operational with SQL Fire. And you can get a much more predictable latency and a very nice scalability profile. So we conducted another test. And this was a much more elaborate application, which is Sprint Trader. Are you guys familiar with Sprint Trader? So what it does is just stock trading application that has a couple of components, the application services and the integration services. So they're running on TC server, and they communicate to each other using RabbitMQ, which is a messaging server. Now, the application services exposed a REST API that web clients and mobile clients can consume to say, do a query on your portfolio, or buy or sell a given stock. So whenever you're querying your portfolio, the web application goes straight to SQL Fire. But when you need to do some more complex processing, the web application delegates that to the integration services. And that's where the web application pushes a message to RabbitMQ, and the integration services, on the other hand, is waiting for that message to arrive, and they do the complex processing, do the update of the results back to SQL Fire. So that's basically what Sprint Trader is. And for this particular test, we created a number of small VMs. So the application tier and the messaging tier, they have VMs with 2 vCPUs. The application tier had 1 gigabyte of RAM, and the messaging tier had 2 gigabytes of RAM. So very standard, small size JVMs. On the other hand, SQL Fire had 2 VMs, one with 8 vCPU each, and 96 gigabytes of memory. So the results were here. Now, we are going to talk about in the context of the application services. So how the application services responded and how they were able to scale under a particular amount of load. So here, we're presenting the scalability test results, and in the y-axis, we have the number of users. And the horizontal axis has the number of VMs just allocated for the application services. So first, we started with 1 server. After we run the load test, and the VM number 1 reached its capacity, we added VM number 2, number 3, and number 4. So after adding 4 VMs, we were able to obtain, with this topology, 10,400 user sessions. So that's pretty good. And that translated into 3,300 transactions per second, just with 4 VMs with 2 gigabytes of RAM and two vCPUs. Now, we wanted to find out also the response time. So we took every single page on the web application and then started running the load. So here you can see in the y-axis the number of seconds it took for the number of users on the horizontal axis. So we got a consistent response time for the same amount of users, the 10,000 users that we were talking about earlier, and we got 250 milliseconds, end-to-end response time. So, and that's because RabbitMQ and SQL Fire move pretty quickly. You're going to see that in the demo. But at some point, the response time started increasing, and that's because the CPU of the application services became a bottleneck. But you can easily solve that just by adding more instances of the application services. So key takeaways, you can certainly scale different, with a very nicely architected application like Spring Trader and a good runtime platform running behind it, you can certainly start scaling independently the layers and doing that on demand, and then you're going to get a much better performance and also a very nice scalability profile. Right, back to you, Emad.
Okay, so thanks, Guillermo. Actually, one thing I wanted to add, part of that performance study, I actually love reading that performance study. It was done by a colleague of ours, Hal Rosenberg. If you download the VFabric reference architecture, we have a reference to it in the slides. Topic 3, document topic 3, is the whole performance study. And it's pretty extensive, shows the way RabbitMQ behaves versus SQL Fire versus TC Server and so on. And I recommend you guys download a copy of it. Okay, so let's get into more kind of GC tuning. The other section early on was on sizing and then performance. So what am I seeing out there in the market? I see most customers are comfortable with sizing a 4 gig heap these days. There's a joke going around these days is that the 4 gig is the new 1 gig. And that's kind of true, right? And within that, you're probably looking at about a 2 vCPU VM, whether it's on physical, you need 2 CPUs, physical CPUs, or 2 vCPUs on virtual. The reason for that is probably at steady state, when the application is not really running that hard, you probably don't need those 2 CPUs. But at peak time, when GC activity picks up quite a bit, it's going to chew up an entire pCPU quite easily. And so then you need an additional amount of CPU for your regular user transactions. But what about large JVMs, right? You can't really put very large JVMs on a 2 vCPU machine. You need 4 vCPU plus. The reason for that is because when we tune, and I'm going to show you later on JVM tuning, when we tune large JVMs, we use a combination of concurrent mark and sweep in the old generation and the parallel new GC in the young generation. And the parallel new GC in the young generation uses parallel GC threads to scale up. And those parallel GC threads, basically, if you had a 2 vCPU machine and you allocated only 1 thread to the parallel GC, that's no longer scalable, right? It becomes a serial GC. So you need a minimum of 2 parallel GC threads. So if you take 2 parallel GC threads, then what about the rest of the application or the transactions running on that JVM? Those need CPU cycles. So it turns out that 4 vCPU machines are absolutely the minimum for large JVMs. What do I mean by large JVMs? It is workload dependent, right? But from what I see out there, anything in the range of 8 to about 128 has to be on a 4 vCPU plus. Probably if you get 128 gig, you're talking about 8 vCPU type of virtual machine. Okay. So as far as virtualization, you get some vendors will say, well, this application server is not certified on this virtualization hardware and so on. And none of that is true, because as far as the hypervisor is concerned, it doesn't even know Java is actually running on the virtual machine, let alone with GC, right? And as a result, we've written a lot about GC and tried to kind of educate our customers about what's available within the GC space. If you look at GC types, and I'm focusing on HotSpot here, and later on I'll show you some of the IBM J9 GC policies. You've got really 4 types. You've got the serial GC, the throughput GC, and the next slide you've got the concurrent GC and the G1. The serial GC is basically what you've got on your laptop. It's for single user mode. It's not scalable, but it's good enough to run up IDEs and so on. And it's known as the stop the world GC. When GC activity runs, everything stops. Yeah, we can't do any other regular user transactions. The throughput GC is like the serial GC, but with parallel threads, the parallel GC threads. Basically, each parallel GC thread is an additional worker that wakes up to do cleaning, GC cleaning. So the more threads you have, the more cleaning activity, and it does chew up more CPU. Now in the demo, we're actually going to show basically what we mean by adjusting young generation and impact of parallel GC threads, but we'll save that to the demo. Then, and by the way, the throughput collector in the previous slide is the default GC policy on server class machines. So if you have a big server and you put Java on there, automatically the default is the throughput collector. And the throughput collector is good enough for most things. You switch to the CMS collector when you can't get after a huge amount of tuning on the throughput collector, you can't get the response time, then you switch to CMS. And pretty much these days, I use CMS everywhere. I'm pretty comfortable with it, and I'll show you some JVM tuning so you guys can use. So with CMS, they call it concurrent, right? Versus throughput is parallel. What is the difference? It's concurrent, meaning it runs alongside of your application threads, doing GC collection or GC activity alongside of your application threads without pausing your application threads, right? Now, some of the JVM purists will say, well, it's mostly concurrent because it's multi-phase and there are 2 phases where it actually has to lock at some point and pause. That is true. There's the initial mark and the remark phases of CMS. Basically, those are pausing. But when you look at in the grand scheme of things, those pauses are so short that they don't even register on the scale. Now, the CMS algorithm, the most recent algorithm, certainly since Java 6 update 29 plus and then on Java 7 is pretty good. Early on, had fragmentation issues and it couldn't scale. If you have not tuned this correctly, you will get into what's known as concurrent mode failure, which means CMS is not able to really apply its multi-phases and it defaults back to the throughput collector. So in the logs, if you see concurrent mode failure, it's time to tune the JVM. And then G1. I still don't see G1 being used in production systems, but we'll see how that changes. OK, JVMs are literally tuned around 2 concepts, right? Either you're reducing the amount of latency, right? Or you're tuning for better throughput. And the type of workloads that care about latency is kind of big web applications. Job schedulers are kind of care about throughput, as we mentioned earlier. And then, for example, in-memory databases care about latency. So one of the unique ways of getting good latency and good throughput along that blue line, kind of good medium between enough throughput and good response time, is using this combination, par new GC in the young generation and CMS in the old generation. And what we're trying to do here is try to fit as much as possible these green threads, application threads, in between all of the GC activity, right? And then survivor spaces, obviously. We'll talk about survivor spaces a little bit later. So when you're tuning a GC, what do you want to measure, right? Obviously, you're going to get into some tuning. What are kind of things you want to measure? You want to measure the frequency of minor GCs and then the duration. And same thing in the old generation. And these are your 4 numbers actually you're playing around with the whole time. Because as you adjust the young generation and adjust the heap, you're impacting how many GCs you're getting and the width of it. And I'm going to show you in the next few slides the impact of adjusting young generation. Now, it turns out that over the last 15 years, the amount of tuning I've done, in the earlier days, it used to take me about 7, 10 times to try and, in terms of iteration, to get the tuning right. These days, it's down to about 2. And I went back, kind of looked at my notes, and picked out, of the ones that worked really well. And I noticed a pattern, which is whenever you attempt GC tuning, step A, you tune the young generation, which is the single most powerful tuning flag, and we're going to show that in the demo, without really touching the old generation. Just focus on tuning the young generation, which is minus XMN adjustment and parallel GC threads. Minus XMN adjustment affects the frequency of minor GCs. So if you want less frequent minor GCs, you adjust the minus XMN up and vice versa. And then parallel GC threads impacts the pause of the minor GC. So if the pause...
How do you determine how to set this XMN?
Yeah. So most Java applications these days use a lot of the, a lot of churn in the young generation. It turns out the tuning that I see out there is anywhere between 10% young generation to about 33% is minus XMN. And somewhere in there is the sweet spot. Now, when I do the tuning, I start at 33%. And if I have to adjust down, I'll adjust. But typically, I leave it at 33% and leave it at that. Now, in the demo, we actually do that. We are going to show that. We're going to show 10 meg to, we're going to show like, what is it, 5%? Yeah, to 30% and see what the impact is. But start at 33%. And then once you're done with young generation tuning, which really impacts your response time throughout the day, right? We move to old generation tuning. And in old generation, I've only got minus XMX to adjust, and maybe initiating occupancy fraction in CMS. And so step A and step B is more than good enough tuning for category 1 applications. Remember those applications that have thousands and thousands of JVMs? It turns out that in category 2 type of applications, you have to visit a step C, which is adjusting survivor spaces. And that's an intricate kind of activity, only because with very large JVMs, survivor spaces could be multiples of gigs, especially if server crashes in the middle of a discussion. So yeah, you have to kind of adjust minus XMN and survivor spaces, right? Let's take a look at the impact of adjusting young generation. What happens if I increase young generation? Here I've got 3 pauses, 3 collections, and 2 full GCs. If I increase the young generation by 10%, the Eden space is much larger, and there's more space for things to move around. The activity of cleaning is delayed, and as a result, I lose one of these frequencies, one of these GCs. This is great. When we're tuning, we want to see plenty gaps between minor GC activity. And minor GC activity, it's milliseconds. It's happening all the time. So a gap of a second is a big deal because you can put probably 5, 10, 20 threads in there of application threads running happily before they hit this and they get blocked. Now, what is the impact of increasing young generation? There has to be a cost, additional cost. The other cost is these 2 minor GCs that were left over actually pause a little bit longer. But we don't care about that so much because the pause is much less than this gap, and we're after this gap. Now, because we increased young generation by 10% and did not adjust minus XMX, there has to be an impact on old generation. So because now old generation is smaller by 10%, because this is bigger by 10%, it is likely that you get an additional full GC, because old generation now has less space. Now, that typically is actually OK, because the gap between these 2 is probably hours away, right? And we don't care. We can get many transactions done. If you don't like that, then adjust minus XMX upwards by 10%. So if you adjust minus XMN by 10%, adjust minus XMX by 10%, right? And then what about this pause that was increased, right? Because Eden space was longer, was larger. What do? What is the recourse here? Well, if you've got plenty CPU cycles left, adjust parallel GC threads up. Just keep on adjusting it up one at a time. So you start at 2, 3, 4, and so on, right? What about going the other way? What happens when I adjust young generation down, right? Well, the impact of that, because Eden space is much smaller, I am going to get much more frequent minor GC. Now, why would I be adjusting young generation down? Well, there could be situations where, 33% of 100 gig is 33 gig, right? That's a huge young generation space. And it could be that you really don't need all of that. You're not using most of it. So we adjust things down, right? But typically we don't, right? Typically we set it at 33%. But certainly if you did, this is the impact. Now, because we reduced minus XMN by 10% and reduced the size of Eden, the old generation is kind of bigger by 10%, right? Which means these full GCs will take longer because the old generation space is larger. And to mitigate that again, adjust minus XMX down. So it's like young generation is like a slider. Young generation is here, minus XMX is there. So if you adjust young generation by 10%, bring minus XMX with it. If you go the other way, adjust minus XMX up. Now, there are times where you break that rule, but typically this is the main rule. And then survivor spaces. Now, survivor spaces are sized by the young generation over the ratio plus 2. Typically, anywhere between 6 to 8 as a survivor ratio is good enough, right? And survivor spaces are basically still inside the Eden space. So when would you adjust survivor spaces? Let's say I did step A and step B. Everything is cool. There's a little bit of survivor space usage that's not that great. Survivor spaces are too big. And I want to further improve the response time. I will go ahead and increase the survivor ratio in order to reduce the survivor space. There's an inverse relationship, as you saw in that formula. And I'm going to do that here. By doing that, I give Eden space a little bit more space to get things done. And I eliminate some frequencies. Of course, there's a little bit of a cost, because anytime you increase Eden space, the leftover pauses are a little bit longer. But again, as I said, we are after this gap. Look at this big gap that we've created here. So if you adjust survivor space down, what is the cost of that on the old generation? It causes increased tenuireship, right? Because now objects cannot live in here long enough. They have to get migrated over to old generation. Now, moving objects within young generation is fairly quick. It's a reference type of movement. While moving from young generation to old generation is a copy, and it's more expensive. But since we've got plenty space and time here, causing additional migrations to old generation, it'll give us this additional full GC. But because there's hours away, we don't really care. And most of the time, we actually tune the occupancy fraction to be about 75% for CMS to try and delay that CMS activity until we've made it through the peak transactions of the day. So really, it's all about creating gaps to fit these transactions in. Here, I'm showing a 30 gig. Basically, CMS occupancy fraction is 75%. Let me back up a little bit. I've got 30 gig initial max heap. Young generation is 30%, 10 gig. Use concurrent mark sweep in old generation. CMS only works in old generation. And then par new GC in young generation. And this works hand in hand with parallel GC threads. Because those threads only apply to young generation when you're using the CMS and parallel GC type of combination. Now in IBM JVM, it's pretty similar. The default is opt throughput, which is really not that scalable. So when you push out application from development to production, you want to make sure you're at least on this, which is like the throughput collector. It's called opt average pause. Or latency sensitive kind of, let me just animate that through. So Opt average pause, probably like job schedule, small web applications. Large web applications or in-memory databases, you want to use the GenCom policy. When using the GenCom policy and combination of large pages, you want to be careful about that. Sometimes you can get into fragmentation issues. Always turn on GenCom policy or CMS first and get your performance numbers out of that. And if you can't get your performance numbers out of that, then consider large pages. And with that, probably is demo time, right? They've seen enough slides. OK, I'll hand over to Guillermo for the demo.
All right, guys, so this is where the rubber meets the road. So let's start first by showing you what is Sprint Trader and what are the different options that we have. So the reason I'm doing this is because I'm automating the same steps I'm going to show you in a JMeter script. So let's start by exploring the application. So the web application, as you can see here at a glance, will give you the different asset distribution and a summary of your holdings and a summary of your recent transactions. Now, the steps that I automated are related to trading. So as you can see here, there are a list of holdings, and what you can do from the web application is sell this particular stock. Now, whenever you hit the sell button, what's going to happen is RabbitMQ will receive a message from the web application, and the integration services will be listening for those messages, and as soon as it receives that message, it will start a sequence of processing that is orchestrated by Spring Integration. Now, whenever that happens, the results will be stored back to SQL Fire. Does that make sense? Perfect. Now, let me show you JConsole. The first run that we are having, it has the XMN setting configured to 10 megabytes. So as you can see here, the chart shows the exact setting that I'm talking about. And some interesting aspect is that I haven't done anything yet with the application, but TC Server and the JVM have spent 11 seconds working on this with over 1,000 collections. So, remember what Emad said in the previous slides, where he said that the number of collections when the young generation is smaller, it's much more frequent. So that's exactly what he was talking about. Now, like I said before, SQL Fire is basically data grid that is SQL compliant. So for any application like Sprint Trader and for any SQL tool like Squirrel or what have you, all you need to do is to provide a JDBC driver and provide a JDBC connection string. So in this case, the protocol is called SQL Fire, and this is my local host, and the SQL Fire locator is listening on this port. Now I am going to connect, and I am going to select the NanoTrader user, which is the schema that we will be using for this demo. And you can see here that we have a number of tables. For example, the account table. We look at the row count or the content of the table. Again, it looks and feels like a SQL database. So it's very easy for existing applications to start leveraging this ultra low latency data grid. Okay, now let me show you what I have for JMeter. So this is the JMeter script, and here I am automating basically the steps that I show you. First, I'm logging in, then I'm selecting a particular stock to buy or sell, and I create a buy HTTP request. So I'm invoking the REST API that is exposed by the web application, and also I have the sell HTTP request, which is again exposed by the REST API that I just mentioned. So we are taking information from a CSV file, and the JMeter script is going to randomly generate requests for us. So the first thing I'm going to do is run this test a couple of times so you can see the average latency and the throughput for the application running on a TC server instance with 10 megabytes of young generation. Okay, are you guys ready? All right, so what I need you to do is help me out a little bit writing down the average latency and the throughput, because my memory is not what it used to be, so I'm a little bit old, and I won't be able to remember those numbers. So please help me out, okay? All right, so I am going to generate 2,000 requests, and I need you to capture the information. So as you can see, we're getting an average latency of 94, and a throughput of 160, almost 166 transactions per second. Now, did you guys capture that? Perfect. Now, let me run this one more time because the JVM is just warming up. So let's see that the second run is gonna produce a little bit improved average latency and throughput as well. So I'll stop here, and here we're capturing an average latency of 47 seconds and a throughput of 306 transactions per second. Now let me do something else. So what we want to show is that when you have the right size in terms of young generation, you are going to get a much better latency and a much more interesting throughput. So let me do this. So what I'm going to do is first change the value of the young generation. I need to stop the current TC server instance running the web application, and also I need to, and then I need to restart it. So I have script that does exactly that. So we just need to run this. Now in the meantime, I'm going to show you JConsole. So JConsole has the numbers because I just stopped the server. I got this message, but let me just show you the number of collections that we're getting with the young generation of 10 megabytes. And also, you saw that it used to spend 11 seconds. Now it's spending 16 seconds. So, we can explore the other areas of memory, but, for the most part, all right, so let's see if the application came back. So the application is ready to go. And let's generate additional load. So now the application has 164 megabytes for the young generation. And let's see what type of latency and throughput we are going to get with that. So for 2,000 records or for 2,000 transactions, we are getting 57 seconds of latency and a throughput of 258 transactions per second. So that's slight improvement compared to the previous run for the young generation with 10 megabytes. Now let's do another run. So for that second run, let's see how much we're getting. So now the throughput is much better. It is 421 transactions per second, and the average latency is 26 transactions per second. So that's pretty good. Now let me show you, I want to show you JConsole. Let me go back and find out the process ID. That is 5063, which is this. Now let's take a quick look at the young generation space. Now, there's a huge difference. So the garbage collector just spent less than half a second or a little bit more of half a second doing garbage collection, and it has 78 collections. So, if you compare to the 1,600,000 collections from the previous configuration, that's a huge advantage. And that's basically what you know, it's given us this better latency and improved throughput. So, you know, the things that I wanted to show you is that there are ways to monitor while you're running the performance tests. There are ways to monitor how TC server and your application are doing, and also how the messaging server is doing. So we have the RabbitMQ console, and the RabbitMQ console will show you the number of messages that have been processed over time, and will also show you the resources that are helping RabbitMQ do its job. So, you know, very low memory usage and very low disk space usage as well. Now, if you really want to see what's going on with the application, you can certainly use Spring Insight, which is a web application that comes with TC server, and will allow you to monitor a given application and all the servers where that application has been deployed. Now, because we were using the REST API, the REST API is or resides within the NanoTrader services. Now, the NanoTrader services will have a number of endpoints, and if we take a look at these endpoints, we will see the you know, the different response times and how much throughput we're getting. So let's take a look at this order controller, and then we will see that here, the first run with TC server running with 10 megabytes of young generation, you'll see that, you know, our throughput was yeah, you can see that our latency is much better with the second run, and that's because we stopped the instance and then we were able to increase the young generation to 164. Okay, so now let's take a look at Squirrel. There should be more records, and that's basically what I wanted to show you. So, you know, usually you have to do a number of tests, different configurations, but you know, testing will help you understand what is the, you know, based on your requirements, what is the optimal configuration of your JVM to attain the average and throughput that you're looking for.
Let me just switch over here. We ran it many times, and notice we wanted to be fair. You know, we actually warmed up the JVM, right? You always have to warm up the JVM because, you know, the GC cycle takes time. So we did 2 iterations, right? We could have really bluffed the situation and just ran once in the first time and twice the second time, but no, we legitimately ran the first test twice and the second test twice. So we took warm-up into account. And what did we find? You'll find we basically improved the response time by about 55% and improved the throughput by about 10%. So it is true that -XMN adjustment is all about trying to return a better response time to your users for those large web applications or in-memory databases that care about latency. And then at the same time, 10% better throughput. Now, we did it on a small JVM, right? I mean, it's a half a gig JVM, right? And we went from, what was it, 2 or 5% to about 25 to 30% adjustment as Guillermo was running those scripts. We wanted to kind of make the demo quick. Obviously, that relationship applies as you vertically scale up the JVM. The benefits of adjusting -XMN and a 10 gig JVM and a 100 gig JVM, the relationship would almost certainly look like this. Okay, so we have some best practices here for you guys to refer to. A lot of the work that we talked about today is in the VFabric reference architecture that's here in the SQL best practices guide. The VFabric reference architecture has got, some 15 topics for you to look at. There's code that's on GitHub that comes along with it, and about 750 pages of technical documentation. There's online YouTube videos showing you how to install and configure things, about 4 hours worth of different videos. Highly encouraged for you to kind of go through it. Let me see. Are there any questions? Yeah.
So the company I work for, they create a bunch of what they call blueprints, virtual machine blueprints.
Yeah.
That they'll use across all services. Now they may have like a small, medium, large, extra large.
Yeah.
Thing. Do you have guys against having common blueprints for
No.
enterprise-wide applications?
Yeah. Oh, which company is that?
It's an insurance company.
Okay. So, okay. Yeah. So let me kind of repeat the question for the recording. The gentleman's company is an insurance company, is got an in-house best practices of saying small, medium, and large type of blueprint sizing for their virtual machines and JVMs, right? Actually, I'm for that because it creates some kind of method to the madness, right? Now, you want to take care of 80% case that falls into low, medium, and high. And then there's always the 20% case that's some odd workload that you need to tune differently. In fact, if you go to the VFabric reference architecture in topic 3, a lot of the performance studies that Hal Rosenberg and I did is exactly that. There's a chart there that says, if you want to run for 3,000 users, this is what your configuration looks like. 5,000, this is what it looks like. 10,000 users, this is what it looks like. Low, medium, and high. Because a lot of the time, customers don't even know how to size their Java platform, and they need something to get started with. So download topic 3 out of VFabric reference architecture and go through that doc. 10 minutes, okay. Any other questions? Question over there?
Do you have any thoughts on JVM GC? Using tenants was to simplify some tuning effort?
Yeah. So the question is, do I have any opinion on GC? Sorry, say that. Oh, G1. Okay. Do I have an opinion on G1? I think it's very promising. I don't see it used in production that much. So with G1, let me explain G1. So basically, G1 goes from what you had is generational garbage collectors, young generation, old generation, the whole serial type of movement of objects, right? G1 takes a different approach, takes a kind of a grid cellular approach to creating different regions and, using their own kind of algorithm to clean out certain regions quicker than others, right? I do not see it used in production yet. We're doing some internal performance studies with it. We're not ready to kind of release those. I did this performance study that we did it on Java 7, update 25, but I used CMS new GC. And I'm not ready to make a statement on G1 because the numbers were not as good. So, yeah, I wait maybe 6 months. Yeah.
So if you're going to tune this, if you're an active tune, what would be the safest thing to start with? What would you change first?
So let me repeat the question. If you are going to attempt to tune, what would be the safest thing to start with? That's a pretty complicated question. It just depends what problem you're dealing with. I think don't tune for the sake of tuning. Start with a problem at hand. So is the problem throughput problem? Is it a response time problem? Is there a network latency problem? It just depends on what the problem at hand is, and then work backwards from that, right? Now, if you have very limited information and no one really knows where the problem is, and you have to, you're going live tonight, and you have to do absolutely something, like I said, pull up your resume, show -XMN, and adjust that thing to 33%. Any Any other questions? Yeah.
Where does the memory that's used by objects and accessed by J&I kind of fit into this JVM structure?
It's split. It's split. Some of it is in the heap and off the heap. So once the J&I offloader starts to create, so what happens is as soon as the new Java new operator is done, it maps that to a C new operator, which is a malloc, and that malloc object happens in the off the heap space. Yeah. Yeah. Thread contention. I think you were first.
What's your experience with storing and extending things off heap in direct memory? And do you recommend that versus just keeping things in heap?
Yeah, so the question was, what is my experience or opinion on using off the heap section to extend object allocation and so on? I do not recommend it for the simple reason that I think the JVM continues to get better and rely on the goodness of the algorithm and the bugs being fixed and being improved, because I believe 10 Java developers on a product cannot add code 100, 200 of a platform that's proven itself. And we've really tested that. I mean, there's no way you could tune a 360 gig JVM on a platform that's not scalable. Java is scalable. So I don't need it. If there are cases, specific cases that you need it, then go for it. But 99% of the time, you don't actually need it. And I know there are products out there that do that, and they believe in that, and that's fine, but I don't. And you are next, and then two here. Sorry. Yeah.
On VMware, one thing when you were going through the VMs, you really mentioned info swap. Do you recommending
Yeah.
OS swaps at 0 or very, very low?
No. Never. Whether there's VMware there or not, never is the case. What VMware will do is provide pressure management situations, right? So they'll try to extend the balloon driver by reclaiming memory from somewhere else and give it to you. And if that fails, they'll do compression. And if that fails, they'll end up swapping. Not for Java applications. I mean, it's just, yeah, you never want to see those things. And notice when I did the VM sizing, it said set reservation. That's literally saying, just give me the physical frames out of this hardware and see you later.
So you would set swap space on?
No, not swap space. Set reservation on the memory.
Right, but in terms of an 8 GB VM,
Yeah.
I think the default is 10%, 20% for OS swap. Do you see any advantage in completely disabling OS swap?
No, okay, sorry. You would not disable it. You'd leave it, but you do not want to C swap. Sorry, I misunderstood your question. Yeah. And I think gentleman over here. Yeah.
You mentioned IBM
J9, JVM, yeah.
in your experience, have you done tests on other, of course, open JDK, but other more obscure machines or?
No. Okay, so let me repeat the question for the video. And I mentioned the HotSpot JVM, and I mentioned the IBM J9 JVM. And in my experience, have I actually tested other quote-unquote obscure JVMs? No. I only test JVMs that are used out by the community in production. I focus on production JVMs. And I think I know which one you're talking about, but not to get into pointing out vendors or things like that. The HotSpot JVM is very good. It's very good. I mean, you could keep pushing it. Especially when now they're going to collapse JRocket code base into J8. Really, I mean, things are only going to get better for HotSpot. Yeah.
In production today, you would recommend?
Well, it depends on your workload. I mean, I still recommend HotSpot for production. Yeah. And for large JVMs, very large JVMs. They can handle it. Yeah, there's a question here, and then we'll get to you. Yeah.
So as our application grows, our objects also grow. Do you just recommend increasing XML, or do you suggest some other changes?
Okay, let me repeat the question. As the application grows, object grows, or the other way around. As objects grow, the application grows. What do I recommend? Do I recommend adjusting young generation or something else? Again, it's kind of back to the other question over there. It just depends on the behavior of the application, right? Are you getting enough response time that meets the SLA? Is it not enough throughput? Is there a bottleneck somewhere? Is there a heap leak?
Utilization has gone up and response time has increased.
Yeah, so I would start with adjusting young generation, and then depending on what numbers I get, then I would decide to adjust the heap space or not, right? There was one thing we didn't talk about when I was showing the sizing. You know, increasing the heap is not always the answer, because, for example, when you get a traffic burst of 1,000 concurrent threads for what was modeled as 100 threads, that happens in the off the heap section. So it's using guest OS native memory. And if the response is to, hey, increase the heap, remember when you increase the heap, you're still within the Java process, but you've taken that heap memory away from off the heap. And essentially, you've squeezed out the off the heap section for those 1,000 threads to execute in, and you've made the situation worse. So increasing the heap is a natural reaction for most Java developers, but not always is the right thing to do. Okay, just over here, and then we'll go to you. The wood gen? Perm. Yeah. Yeah, I've seen that, and I would. Okay, so do I have recommendations on perm gen tuning? Set it to the right size and avoid it being collected, is the recommendation. And I typically see that as a bug. And by the way, they are going to make that dynamic in J8, so you don't have to touch it anymore. So in the J9, it's inside the heap, and it's managed dynamically. You don't statically size it. And there was a question back there.
What are some of the key points to consider when you're using JVM that's using EM4J?
Okay. What are some of the recommendations when you're using EM4J on vSphere? So I didn't talk about EM4J and didn't talk about ballooning. What are some of the recommendations? So EM4J relies on one thing, right? The initial heap and the max heap not being set to each other. That's one, because it looks for that opportunity of lazy open space within all generation to reclaim. That's one. The second thing is, when would I use it, right? If I've got thousands of JVMs that are kind of tier 2, not tier 1, but they still need to be up, right? It could be developer instances, could be seasonal QA instances. Then I would apply EM4J to be able to reclaim and kind of overcommit memory, because EM4J allows you to overcommit memory. In other words, you could size more memory within the JVM process than what you have underneath on the physical. I do not recommend it for tier 1 applications where you care about performance, and where the recommendation almost always is to set minus XMS, the initial heap, equal to minus XMX. Having said that, there are caveats to that. I would not put EM4J on an InMemory database, for example, period. Any other questions? Yeah.
Outside of workload differences, have you experienced different tuning objectives between the different JVM-based languages? So, for example,
like Scala and yeah.
Assuming the workload types are the same, right?
No, not a significant differences. Still JVM, right? Yeah. No, not big differences. Nobody's really done extensive study on that. No, I'm thinking I'm usually chasing a problem, right? So I think this is a case where we need to go find a problem, and I usually don't have time for that. So just honestly, nobody's done it, but it would be interesting to do. If they gave me 3 months somewhere, I would do it. Compare Scala to some of the other languages, and see what the object footprint is. I think we're probably chasing needle in a haystack because they transpose to objects anyway, Java objects. Natively is a new operator being executed, and that's it. Right? Any other questions? Questions? Yeah.
Is there kind of a golden rule ratio for XSS when you're sizing the stack?
Yeah. Thanks for bringing up that question. The question was, is there a golden rule for minus XSS, the stack size? So everywhere you read in books and so on, they tell you do not touch the default stack unless you get into a Stack Overflow situation where it means either you used a very verbose reflection algorithm or a framework that uses reflection, like all of them. Then you would touch it to adjust the stack upwards to get rid of the Stack Overflow. If you keep adjusting the stack upwards and the overflow still happens, you've got recursive code that you need to take care of. Because no matter how much large stack you give it, it's going to chew it up. That's in category 1 Java applications because we've got thousands of JVMs, and our objective is within a certain memory space, fit as many concurrent threads as possible. On the category 2 in-memory databases, we go the other way around. We care, sometimes the stacks could be fairly fat, and we want to execute as many objects as possible within that. And what happens is this. And in those categories, in the category 2, we go to like 1 meg, 2 meg, 3 meg, 4 meg. The last I've tested was a 4 meg stack. Reason for that is if you look at modern servers, if you look on the chip, there's the cache register hierarchy of L1, L2, and L3. Okay? This is the actual, before you go into memory, when a CPU cycle executes on the clock, it uses register space. It's L1, L2, and L3. These hierarchies can go up to like 18 meg plus. They're fairly big. So Java has an optimization called escape analysis, and it does inline object explosion. What does that mean? It means it will see that if no other thread is using an object, it will piggyback off the stack to execute, even before getting into memory. And because of that optimization, we have a legitimacy to try and increase the stack to multiples of megs. Yeah? That's kind of a long answer, but.
Yeah,
so the guidance is, between 256K to 1 meg and less on, if you've got like a web application. If you've got an in-memory database, it could be 1 to 4 meg, but it's not a hard and fast rule. Anything else? Any other questions? All right. Thank you. That was it.